The goal of ENME489Y was to provide students with the opportunity to have hands-on experience with the field of remote sensing. Over the course of this project and semester, students used custom lidar instruments to map 3D point clouds of different landmarks around the campus of the University of Maryland. Overall, this project provides students with the opportunity to work on a systems engineering project, as it required students to demonstrate an understanding of lidar physics and fundamentals, the ability to create a custom experimental setup, and then conduct data analysis using data analysis software. So for my target, I chose the animal science bench that's located in the courtyards of the animal science building. And so I chose this target because it's on the path to ENME489Y. Every morning I would actually go up Engineering Drive and always take this path. So I always would pass this bench every time I had class. And I thought it would be a very cool target to take data of, especially considering all the really neat patterns associated with it. When we talk about remote sensing, we have to consider two different methods: passive sensing and active sensing. In passive sensing, there is no generated radiation source, whereas there is one with active sensing. In passive sensing, it usually relies on some naturally occurring source of radiation, such as the sun, where there's solar radiation that travels through air and then hits a target, and then it propagates back through air, which is then now the signal is received and by our detector, and then we can do data acquisition and data analytics of this collected data. With active sensing though, we have now a generated radiation source, which instead of the sun, it could be a laser, now sends radiation through a medium, usually air or water, and then it interacts with the target of interest, and then we have the signal propagate from the target, and then that's received by our detector, and then again we can do data analytics and data interpretation. LiDAR, or light detection and ranging, is an active remote sensing method. We take a look at the image on the right, and we use this plane measuring the altitude at which it's flying as an example. The plane has some sort of radiation source on it, and then it'll send out a radiation pulse, which is represented by the red arrow in this image. It will then reflect off the ground, and this reflection is then at the point that it hit the ground at position 2, and then it will reflect and then be received by the plane. This reflected pulse is represented by the blue arrow in this image. Now, for the plane to truly measure how long the distance at which it's flying, we use the range equation, which is represented by c delta t over 2, which c is the speed of light. Delta t is the time it took from the plane for the light to leave the plane, reflect off the surface, and be received by the plane again. And so we can use that distance to then determine how high the plane is flying, or how far away a target is. So computer vision is a way that computers can gather data from images and videos. So in this example, I show how using Python and OpenCV and a combination of filters through OpenCV, I can isolate the color green, and I can then pinpoint it and target it as I move it around in this video. I can see how this will be a powerful tool in later data collection when I'm looking for other specific colors, specifically red in later data collection videos. In my LiDAR project, we now used a combination of hardware and software. On the hardware side, we used a custom-built LiDAR test setup, which was used to house a line laser, which can be seen as the LiDAR radiation source. And then we used also a Raspberry Pi camera, which is seen as the LiDAR receiver. Then on the software side, we used Python and OpenCV. OpenCV was the computer vision software that was used to analyze the images that were taken using the Raspberry Pi camera and correlate them with distances and range data. That range data could then be used in Python to create a single 3D array and matrix that can then be used to create a 3D point cloud of the target. Some of the important hardware include the line laser, the Arduino, the Raspberry Pi, the Raspberry Pi camera. The line laser allows for multiple points to be recorded rather than just one. The Arduino supplies power to the line laser. The Raspberry Pi serves as the microcontroller of the entire process, and runs the code that is recording all the data. The camera is what serves as the LiDAR receiver. In the case of this project, we employed a geometrical lidar technique that was rooted in the fixed distance between the camera and the line laser. The camera would take an image that would also capture the line laser beam. The center of that image would correlate with the camera. OpenCV would then detect the light reflecting off the target and detect the location. The greater the number of pixels between the reflected light and the image center, the closer the object. As just discussed, the lidar setup for this project determined distances based on pixel counts. However, the setup required calibration. This image shows the single beam configuration based on a single laser beam rather than a line laser. And then the laser is separated from the Raspberry Pi camera by a distance of 12 inches. And this would have an effect on the theoretical ranging data. Several distances were recorded, which are depicted by the red dots in this graph, and using the single beam configuration, and they are then compared to the theoretical values, depicted by the blue line. Seeing that we have good agreement between experimental and theoretical data, we could then proceed with the line laser configuration. The line laser configuration required similar calibration, but alignment was also required for further testing. Seen in the image on the left, we show an image with a series of vertical green lines that serve as alignment guides. To capture the most representative data, I had to align the line laser with the green lines. So in this example, the red laser of the line laser is aligned well and is parallel with the green alignment lines. And seen here, we show the line laser setup being used in action. So as we touched upon earlier, we want to use a combination of Python and OpenCV to extract distance measurements from the JPEG images that are captured with the Raspberry Pi camera. And so in the beginning, we first define the upper and lower bounds of the red line laser color, because in the JPEG images, we want to be looking for that color so that we can get distance measurements from it using the calibration code and the geometrical lidar strategy as described earlier. And as we move forward throughout the code, as we extract all of the images, the angles from the file names, the JPEG file names that were captured with the Pi, we then move forward to conducting blurring and filtering of these images using a Gaussian blur. And this way we can still extract the distance measurements we're looking for, but without sacrificing processing time. And then we use that mask defined by the upper and lower bounds defined earlier in the code for the red laser. We can then start isolating it. And then as we showed with the stoplight, rather than looking at green, now we're looking at red.
So now I'll demonstrate a sample data collection with the Pi. So right now we're at about 1 degree and using my phone level. It's now looking here at the code. I'll run it, and now it's going to wait, and now it's going to ask me for an angle. I'll input that. It'll confirm. Now it's going to try to capture an image of this degree capture, and after 5 seconds it'll cancel. It's now stored the picture, and now I'm done. Here is a full scan of the front side of the bench as we move from the bottom to the top of the bench. So since the bench was too long for the lidar to pick up in a single scan, I had to divide the front and back into 2 scans. So first I collected data on this side of the bench. I then collected data on this side of the bench. I collected data at this angle. I collected data at this side of the back of the bench. And I collected data here. And finally, this was my last position, I collected data here. So for the data collection of this animal science bench, I did not encounter too many problems. With the resolution, all the data collected was within reasonable scale, within reasonable magnitude. The only, I guess, real problem with collecting the data was that for 4 of my data collection sites, 1, 2, 3, and 4, they were all on very flat ground. Then on the back images for 5 and 6, then I was on mulch, which was a much more uneven surface, so it was a little more difficult to balance the lidar and make sure it was still aligned. So for all of those data collections, I had to make sure I aligned the lidar each time that I took data.
So after collecting all of the images at the test site, I then would want to then save them onto my computer so that I can then do data processing to create a 3D point cloud. I use CyberDuck as a way to access the files that are located on the Raspberry Pi and then transfer them onto my home PC. And I would SSH in through my Pi, and CyberDuck would allow me to do the same as well. So then I would go to PyCharm. PyCharm is a way for me to use a Python IDE so that I could be able to use Python alongside OpenCV coding so that I could then use all of the images that I collected to then read out distances for all the different points that the line laser was targeting for that data set. And once I was able to determine all the ranges and distances that were calculated from PyCharm, they then would spit out a final XYZ matrix, and then it would then spit out a 3D point cloud. Preferably I used MATLAB. MATLAB was a way to better visualize the data. So here's the data compiled from all the 6 scans that were taken at the test site. Each different color represents a different scan type, so that's why we have 6 different colors. So if we take a look at this image, we don't really see any sort of representation of the bench. So now we knew we had to do some additional filtering because we see we have these extra points that we aren't really representative of the bench. And then we also see how that we don't have a bench here. We'll need to do some moving around of the data sets. So to do so is I picked a single data set and then I oriented and moved around all the other data sets to align with the origin data set. And so once that was completed, I could then complete the data compilation, and I was able to produce this image. So now we see a much more representative image of a 3D point cloud of the animal science bench. By moving around the data and filtering out some of the unnecessary points that could have been produced by noise or scattering, we can get a much clearer representation of the bench. And we see from the 3D point cloud we can actually pinpoint the gaps in the bench, which are from the pattern of the bench. We see the knobs of the armrests of the bench too, and then we also get a sense of the depth of the bench. So all in all, this is a pretty good representation of the animal science bench. The only difficult areas seem to be the bench legs, and there was some noise on the yellow data set, but overall this is a very good representation of the bench. So from before we saw how we stitched together all of the points and created all the scans. So now what I wanted to do is I wanted to create a single text file that will compile all the data. So what I use is I use the concatenate function, cat function, and where I just place each one X, Y, and Z to create their own single arrays. And then what I did is then I moved down and I put them all together. In MeshLab, I then could create a mesh. And so once I had all the points in, which are represented by the yellow dots here, I could create normal points to all of these, or normal surfaces, the normals to all of these points. And once I've done that, I can then create a surface, and I wanted all the normals to be as aligned with each other as much as possible. And then I could create the mesh surface, where here is the best one I got. We hide the normals, we can see a little bit better. And so it's some things to point out are that it was clear that the image was able to, that the mesh was really able to pick out the depth of the object. But as we saw with when we created the point cloud, it could create the difference because it could measure the start of the bench and the back of the bench, but anything in between is a little more difficult to capture. So that's why there's these divots here, because for my best guess and interpretation of the software is that it's trying to fill in the gaps, and this is the best way it can do that. Another cool thing is it was able to pick out the arches of the handles of the bench, and I wasn't able to pick out however, it wasn't able to pick out the pattern in the bench as well. And so this is the best representation I can get by converting the point cloud into a mesh surface using MeshLab. that's it. Thanks.